Good morning, everyone. Today and this week, we are going to continue with OpenGL, and we are going to talk about programmable shaders. And this is the start of the last 3 weeks of classes. So the plan for these last 3 weeks is that we are going to finish. We are going to talk about how we can do these programmable shaders in OpenGL, how we can do texture mapping, how we can generate dynamic shadows. We are going to also talk about shadow mapping in OpenGL, that algorithm, how we can implement that. And the last week we are going to talk about curves and surfaces, which are not necessarily, we are actually going to use some linear piecewise approximation of those curves, but we will start with an infinite resolution mathematical equations that make up that to model these curves. The last week, the curves and surfaces topic may be useful when you want to, for example, generate paths that pass through a smooth curved path that pass through a certain number of points, or if you want to do some cloth animation like a flag, you can also use curved surfaces to generate the flag. This is going to be the last week's topic. As I said, we are going to continue talking about OpenGL and programmable shaders this week. The examples I provided on AutoClass actually contains examples regarding this week's topics and also the following weeks, like texture mapping. There's an example that does texture mapping. There's an example that gets the depth buffer and writes it on a texture. The depth buffer is written on a texture. This is what we are going to be doing in shadow mapping. So it contains all the examples are already comprehensive and contains everything we are going to learn about OpenGL and programmable shaders. And yeah, and the last week it's going to be curves and surfaces, as I said. If you have any questions regarding any of these, if you had, I hope you were able to get yourself development environment for OpenGL, either on macOS, Linux, or on Windows, as we did here in class. So I just downloaded the examples again from AutoClass, so that you're not looking at some examples I may have already modified. So I'm just unzipping the ones that I already shared with you. So we are going to, some of the topics we're going to talk about today, we are going to take a look at these examples again. All right. So the way we talked about GLFW on slides, this is where we left on slides. I'm going to finish these slides today, and we are going to also start talking about programmable shaders, which we already have seen some examples. So the way we send geometry data to GPU, so after we have our window, the next step is to issue drawing commands at every frame. So the first command will be to clear the entire frame buffer to start up painting from scratch at every frame, and this is done so fast, and since we use double buffering, we see actually a smooth animation if we have dynamic things that change in the scene, like the camera angle or certain objects that are moving. These things will appear as smoothly animated because we'll be able to do this thing, sending geometry data. We'll be able to draw things on the screen 60 times per second. If we have, I mean, that's the goal, but for certain scenes which contain very complicated data, or the effects may be, if it's time consuming, you may not achieve that 30 frames per second or 60 frames per second. In that case, you have to do some simplifications or optimizations in your scene to make it simpler and manageable by your graphics cards. But the power of these graphics cards has increased so much in the recent years that, I mean, the graphics cards that we use on a typical desktop, they are much powerful than we had the Silicon graphics workstations, for example. There were workstations designated for graphics type of applications, graphics applications, and the graphics cards we have these days are much more powerful than those. So as I said, after we have the window, at every frame we need to issue drawing comments. One way to do that is, and that's the most efficient way to do that, is to send this when we're issuing these drawing comments, we send actually the geometry data, the data related to the scene should be actually sent once before the start of this rendering loop. But in traditional OpenGL, actually, when these data are sent at the time of issuing the drawing comment. So what you see here, the simple approach that you see here, which is a set of OpenGL commands. So this GL begin, the function calls that have this prefix GL are OpenGL API calls, and GL begin tells the, it's basically issuing a drawing comment saying the GPU that we are going to draw some primitive, and this primitive is here indicated as a parameter to this function, GL lines. So we will be drawing a set of lines. And after this GL begin, we issue GL vertex commands, these functions, GL vertex 3f, which sends one single vertex data. It's the coordinates of single vertex. When we say GL vertex, we mean that we're sending the coordinate data for a vertex. Okay, if you want to send, for example, the normal vector for a vertex, this is done actually by, for example, first there is a command for GL normal. This normal is associated with this vertex in such a way that, we also write, for example, nx0, nx, ny0, and ny1 like this. Oh, sorry, and z0. So when we issue this function GL normal 3f, it sets the current normal vector to be something. So whatever the current normal is, it is associated, when we say GL vertex, that's the place where we send the vertex data, and whatever the current normal is, that is the normal associated with that vertex. So it's like, as I said, OpenGL is not object-oriented at all. We don't have vertices with fields, data fields in it, which we can set color of a vertex, the normal of a vertex. It's like these normals and color attributes of a vertex in a traditional, when you're sending geometry data like this normal vector and color values, they're like global variables. They're like states that you set. Okay, when you say GL normal this is whatever, all the vertices that come, all the GL vertex calls, you may have many of those. Okay, for example, let me write a bunch of vertices here. Okay, by the way, this indentation is only for, as you can see, we don't have any, this is not a block of comment, but in order to say, okay, these GL vertices are between this GL begin and GL end, this is the place where we send geometry data, we usually indent these function calls like this. So when you have 6 vertex calls like this, for example, this normal vector will be associated with all of them. So you just set the current normal to this value, and any GL vertex call uses the current normal vector value as its normal vector. Okay, so this is, so if you want to assign different normal vectors to each of these vertices, you have to repeat this GL normal call just before. You have to have GL normal call preceding these things. Okay, and as you can see, this is not a very efficient way, because these are real, these are function calls on the CPU side. So every time we are sending one geometry data, we are creating an activation record for this function. We go to that function, we return back to execution here, continue with the next function. So the example we had, the Spotlight example, contained this old way of sending geometry data. So this inefficient way is no longer used in many systems. As I said, it's even deprecated in some of the, I think it may be deprecated in newer OpenGL versions, but you may still be able to use them and be able to compile them. Although they're deprecated, you can still have them. This is such an example, as you can see. Within GL begin and GL end, we set a single normal vector, GL normal 3f. The way the function, OpenGL functions are named are, so they're preceded by GL, and it's followed by the actual name of the function, like we are going to, this is going to be about the normal vector. And what, as a suffix, the suffix of this function, this 3f, indicates that it gets GL, different functions have different versions. For example, there's a version of GL vertex which gets 2 parameters only. If you're just going to do 2-dimensional graphics, for example, you can just ignore the third dimension, the z dimension. It will just be taken as 0 and issue GL vertex 2f comments. And this f here indicates the type of the variable, that type of the parameter that you're sending. In this case, it means you're sending floating point parameters. Okay, although I'm sending all integers here, I could have, it doesn't, I mean, those integers are turned into float, and in the normal 3f function we have floating point variables. Actually, I could have, for efficiency maybe, I could have just used, instead of these f, I could have used I here, which is for integers. If you're sending integer parameters, you could just send those coordinates with the suffix GL normal 3i. And as you see here, they're all integers, and it won't make any difference. And when they're integers, but when we do interpolation, for example, during rasterization, OpenGL internally converts them to floating point numbers, but probably during sending of the data, in order to indicate the size of the buffer or how they are sent, this type information is used internally for that purpose. So it doesn't really matter that much whether you're using I or F. I haven't used, when I'm writing these functions, I always use the F, the floating point versions. So in this GL begin and GL end, this GL normal, which is 0, 1, 0, which is the up direction. As you can see, this is a tabletop in which it has a single normal of this tabletop, which is pointing upwards in positive y direction. And all these triangles that are drawn here, that every issue of this GL vertex call, there is the triangle is drawn, and every triplet of these GL vertices are taken as a single triangle. So this after this GL begin, depending on the type of the primitive you're indicating here, in this case it's GL triangle, the GL vertex calls are treated or grouped together in different ways. For example, in GL triangles, every triplet, non-overlapping triplet of vertices are used to draw a single triangle. So here with these two GL vertex calls, I am drawing 2 triangles. Okay, and if you look at this for loop, by the way, you can have for loops within GL begin and GL end. You can issue multiple calls like this. So there are like 301 and 301. So these for loops execute for 301 times 301. So 301 times 301 and times 2. We draw actually this many triangles, 181,202. So with this GL, within this GL begin and GL end, we issue a command to draw almost 200,000 triangles and that many function calls. Okay, so it's it's still very efficient, as you can see, but this is not the efficient way to do that, especially if these values, as you can see, the vertex coordinates u, v, they are all static. I mean, this geometry data is not changing from frame to frame. The geometry, even if you want to move the table around, make the table, scale the table, you can do that, by issuing modeling transformation comments regardless of this coordinate data. The way we change geometry, for example, if you want to rotate, translate, scale down an object, you don't change the vertex data directly. As we have seen, we have a way to do that by using modeling transformations. This data, the vertex coordinates, remain fixed, and before drawing them, if you issue a comment, for example, saying that GL scale F 0.1, 0.1, 0.1, what will happen is that this call is going to update the current modeling matrix by multiplying it on the right with a scale matrix, which is 0, 1, 0, 1, 0, 1 in the diagonals. And during the drawing of these coordinates, what happens is that these coordinates, the current vertex coordinates, are multiplied. They are processed in the vertex processing stage. They are multiplied by the model view matrix before actually being drawn on the frame buffer. So these are going to remain fixed. For example, you can have an animation in which you can change the scaling of this table at every frame. You don't need to change this part. This part remains fixed. So you can actually send this geometry data once at the beginning of, before going into this rendering loop. You can send this geometry data to the GPU. Right now, the entire data is created on the fly with these variables u and v. Sometimes your geometry data is read from a file in terms of XYZ coordinates, and the coordinates remain in some array in the memory. It's in the CPU memory. So before, instead of issuing these comments at every frame, we may send this entire geometry data to GPU memory and then just issue one function call to draw these triangles. So if we go back to this slide, when we have GL lines, what happens is that every tuple of, so every two of these vertex calls, okay, every pair of these vertex calls like this one and this one, this one and this one, so it will draw 3 line segments. If I have it like this, it will 3 line segments will be drawn. Of course, we need to maybe change the coordinates. These are like degenerate lines with, I mean, you don't want to have draw a line with beginning and end point with the same coordinates. So obviously you have to modify these things to be different things, for example. But in GL lines, every pair of those are going treated as a separate line. There are other primitive types like GL line strip. In line strip, these two are treated as a line. If you have line strip, I think it's like this, or maybe there's no underscore in between. I'm not sure about that, but either that one or this one. What will happen is that this will be treated as a line. This will be treated as another line segment. This will be treated as another line segment. So it's going to be these vertices in the middle are going to be shared between the 2 consecutive lines. So it becomes a line strip. There's also other like triangle strip, which you're going, if you have a set of triangles which share an edge between them, which means which share 2 vertices between them. It's like if you have something like this. Okay, so this is a triangle like this, another triangle, another triangle. So look at this. So these are triangle 1, 2, 3, 4, 5, 6. Instead of having 18 GL vertex calls with GL triangles, what you can do is you can define this as a triangle strip primitive, and in that case you have to specify just these 2 vertices will be the 2 vertices of the upcoming triangle. So if this is, for example, 1, 2, 3, the next triangle will be automatically defined as a triangle 4, 2, 1. Because of the winding order, we have to have all of them in counterclockwise order. Actually, I have drawn them incorrectly, not this 1, 2, 3 like this. It has to be counterclockwise. This is 1, this is 2, and this is 3 like that. Okay, the front, I mean, you could have done the other ways, but in that case, the front faces of the triangles will be not facing towards you. Okay, so this counterclockwise order of the vertices indicate that the front face is now facing towards us. And 1, 2, 4, in that case, this 4, 2, 4, 1 is going to be, not, sorry, this way again. Counterclockwise 1, 4, and 2 will be the counterclockwise of these things. The second triangle. It's automatically changed by the triangle strip function. But every after that 1, 4, this is 5. 1, 4, 5 will be the next triangle. Oh. And then actually we can take a look at the GL triangle strip command for that. But what I want to say is there are different primitive types in which you can draw different types of geometry. Attributes beside position can be sent. I've just given you an example of how we send normal vector attribute of a vector. This is like when you say GL color, you're just setting the current color, the global variable, the current state of the color to red, then whatever GL vertex walls you have afterwards are affected by that current state. When they are drawn, they're going to be drawn with red color. This is how GL color changes the color of vertices. These days, when you're writing OpenGL applications, actually, you're not using these global, you're not using it this way. Everything is done by the user now manually, even the color lighting computations. So sometimes you may send color data as an attribute, vertex attribute to the GPU. And however you want to treat that color data, you want to blend it with texture color, you want to compute, you want to treat it as a diffuse reflecting coefficient. However you want to use that color, the user manually uses that color to compute the color of a fragment. In modern recent OpenGL applications, we are going to see examples of those. But this in the traditional way, everything was, in the old way, everything was set, changing the current state, and whatever vertices we have are affected by the current state. So triangles are similar. As I said, we have seen an example of 3. Every group of 3 vertices define a triangle. If you want to draw 2 triangles, you have to issue these 6 calls, 6 function calls, as you can see. Every triplet, every 3 vertices, they will define a triangle. There's this triangle strip example. So 0, 1, 2, when you write this 1, 2, the third vertex here, it's here the triangle is written as 2, 1, 3, as both of them are in counterclockwise order, as you can see. 0, 1, 2, then 2, 1, 3. So when the next one comes, it's going to be again 2, 3, 4 this time. So this is a triangle strip example, and as I said, the winding order is important. The winding order, which is the order of the vertices of the surface, determines which face is the front face of the triangle. Here both triangles are facing towards us. 0, 1, 2 is, as you can see, it's counterclockwise. And 2, 1, 3, it's also counterclockwise. So both triangles, this triangle strip is facing the viewer. And yeah, it is important to use a consistent winding order when drawing a triangular mesh. Because if you're doing it inconsistently, if you have a triangle mesh consisting of thousands of triangles, if you just do this winding order randomly, when backface culling is on, when backface culling is not on, it will not be important actually. You'll be able to view the triangle the same way if it's facing towards your, if it's not facing, if it's facing backwards. But obviously the normal vector is going to be different. If you're going to be doing lighting calculations, again, it will matter. Even if you're not doing backface culling, if you compute the normal vector with respect to this winding order, it will also be problem. Some parts of the mesh are going to be darker if they're not facing the light. Some parts are going to be lighter, more shinier when it's facing the light source. So you have to be consistent in all the front-facing triangles of a triangular mesh should have their vertices correctly ordered in this counterclockwise order. So again, this is a repetition of what I just said. I'm going to skip this. So it's like OpenGL is not object-oriented. It's like a state machine. When we call these functions, the values change the current state of the color or the normal vector. So in this example below, the color of each vertex is set to green, RGB 010. So all of these vertices are green because we set the current color to be green. So it's like changing the pen color of when you're doing something in Paint. Again, changing the normal vector. If you want to change the last vertex to a different color and different normal vector, you have to change the state like this beforehand. There are some typos here. I mean, the semicolons are forgotten here. We have to put them here. Yeah, so this was the examples we have seen are called the immediate mode. And immediate mode is inefficient. Modern applications do not use this immediate mode. It can be used mixed manner. For example, the tabletop is drawn in immediate mode, but the other parts, the table lamp, is drawn with vertex buffer objects, for example. The entire geometry data is actually sent beforehand when we have this init scene. Let me show you where init scene was. Right here. These function calls, line 77, and here line 74, and line 80. So it's sending different types of data to the GPU. So this buffer data command is an OpenGL function which sends this entire set of geometry data or normal vector data to the GPU's memory. It copies whatever we have here in this vertex data. Vertex data, as you can see, is an array. So if you look at this vertex data is nothing but a float array of size 3 times number of vertices, whatever the size of GL float is. By the way, instead of using float, you may ask, why do we have the interesting OpenGL types preceded by this GL instead of GL float? The reason is that for consistency, this basically turned to a regular float on most machines, but I think for portability, since float, the C standard or C++ standard does not necessarily define the size of these float objects as 4 bytes or 8 bytes as a static constant. The C++ standard or C standard just defines, for example, double is at least as large as float. Okay, it may be the same 4 bytes or 8 bytes. This is what the specification indicates. I think this GL, the GL float, OpenGL defines its own types. The API defines its types consistently across systems, so for portability. So when you use GL float, it's in many systems today, it's just treated as a regular float. We could have used regular float here with no problem, but for safety, I think it will be nice to use this GL preceded types. Which are this GL float will nothing but a type def of a regular float in this system, and also this one unsigned int GL unsigned int. But what you see here are the vertex data and normal data are allocated in the CPU memory. And then what we do is we fill those data by reading from some file. Our file contains the definition of this table lamp, the vertices, and the normal vector data. And after that, after we have the vertex and normal data, since this is an index phase format, the next integers, the triplet, actually there's a quintuplet of integers, which is sort of a quadruplet of integers, 4. The first one is ignored, it's just read into TMP, which is just 3. So it's for triangles, it was 3, then the subsequent, the following 3 integers indicate which triangle indices make up this triangle. So we put them into index data. As you can see, we send all this data by saying, for example, I tell OpenGL, generate me a buffer. This is a vertex buffer object, and generate me one buffer, put it into VBO vertex. So this VBO vertex, VBO normal, VBO index, they're nothing but unsigned integers. Let's see where they are. VBO vertex, yeah, they're here. So these are, as I said, this data is going to reside in GPU memory, but from a CPU program, we do not have pointers to GPU arrays directly. I told this before, we have integer handles which we are going to use in our CPU programs, and when we are going to associate the current handle, or we are going to use that current handle as a parameter to certain OpenGL functions to indicate, to refer to certain memory regions in the GPU. So these are just unsigned integers. There are handles. You can just treat them again as pointers to those arrays, but they're nothing but unsigned integers, as you see here. Here with these 3 function calls, we ask the GPU to assign us these handles, integer handles, which I'm going to be using for my vertex data, normal data, and index data. So we just say, for example, I want this VBO vertex handle to be an array buffer on the GPU. I'm going to I'm going to use it as an array in GPU memory. And this is the command where we send that data. We don't need to allocate that. The interesting thing is that when we're binding this VBO vertex to an array buffer, we don't need to allocate any memory on the GPU explicitly. This buffer data command automatically, while it's sending this data, it also allocates the memory on the GPU for us automatically. So this single command, GL buffer data, establishes the sending of the entire vertex data to the GPU memory and allocate the necessary space in the GPU. So whenever we are going to refer to this vertex data, we need to do this binding. So when we are going to do some drawing calls regarding this vertex data, we need to say, now this is the buffer I'm going to use right now. So we are going to do, again, as I said, it's like, this one is also like a state machine. Whatever buffer is currently bound, the accessing of the array or accessing of any data will be done on that array, on that current buffer that is currently bound. So when we are going to send a different data to a different part of the GPU, so we need to bind that buffer data, then this is the command that sends the normal data, this is the send command to send. So these are array buffer, we just put some floating point attributes for vertices, the vertex data, normal data, and this one, this is a different type of an array buffer, GL element array buffer, saying this element refers to the fact that the things that we're sending are indices of the triangles, not the triangles themselves. So it's like it tells us when the GPU is going to be using these element arrays, it's going to actually direct us to actual vertex values. They're going to be indices or vertices that we are sending here. So I don't know why it's specified as different. In terms of data, it's just another array in the GPU, but specifying it like this I think maybe on the GPU it may do certain optimizations, or it may treat them differently. I don't know the inner workings of how element array buffer works, but this is, again, we bind thing. This is the place where we send the entire data. So with these function calls, we send the entire table lamp data on the GPU. So this is the vertex buffer version, the most efficient version. Actually, we could have drawn the triangles again by keeping the triangle data on the CPU memory without sending it to the GPU. There are three ways. Let me show you those. The first one that we have seen is this immediate way, which was using this GL begin, GL end calls, the least efficient way. After that, we have the more efficient way of doing things, GL vertex, using vertex arrays. Vertex arrays. Still, so the data is on CPU here, and sent at every frame. In vertex arrays, data again is on CPU. I haven't shown you this vertex array version. Data is not sent every frame. Data is actually it is sent in every frame, but it is sent in every frame, but we just use one function call instead of many function calls. So this immediate mode has many function calls, many GL vertices at every frame. This one has only one function call, but we still send the data to GPU at every frame because the data is vertex data is on the CPU. The most efficient version is called vertex buffer objects. And in which we send the data once to the GPU. So this was the most efficient version I showed you, was this one, which is using that vertex buffer object. Now, have you noticed these two function calls saying GL bind buffer, array buffer 0, element array buffer 0? This is like for safety. After we finish working with these array buffer and element array buffer, this is like saying this 0 is like the null pointer. If there are function calls, because of the reason that OpenGL is like a state machine, one very bad thing for programmers is that these global states, they are like side effects. When you call a function, for example, you are going to do texture mapping, that function actually sets, for example, the current texture to something. It changes some global state. So everything you do, every function you call in OpenGL has certain side effects. The biggest disadvantage of this is when you have a very big graphics application, big graphics program, things start to interact with each other in an unwanted way. So for example, you may be calling a function, you may just think that you're calling a function, it's doing something on its own. If it changes some global state, it will affect everything that comes afterwards. So it's going to affect other functions because it's changing some global state, right? So this side effect is not a good thing. So one way to reduce these side effects is every time you're doing something, you're resetting whatever you set the state variable, you're resetting back its to original value, saying that now the array buffer is null. So if some function is doing something with an array buffer, it shouldn't assume, if it doesn't set it explicitly, VBO normal will be the current array buffer. If some other function is doing something on array buffers, for example, it will be the VBO normal that it's using at that point. So in order to avoid this, after we finish working on our data or array buffers, it's a good programming practice to reset them back to 0 to indicate that the current state now is null, okay, to avoid this unwanted side effects or effects. So that's the reason of these two function calls. You don't need them every time. I mean, if you're, for example, whenever you're setting everything from scratch on your own at the beginning, you don't need to then set them to back to 0 like this. But yeah, as I said, it's just a good programming convention to do these things. Yeah. Let's go back to this one. So this is after we send that data, the way we are drawing that is we need to, at every frame, we need to enable client state, vertex array, normal array. We bind the vertex buffer and saying that this is my vertex data, vertex pointer. So my GL vertex information is coming from this buffer that I have created previously. In these function calls, we are not sending any data. We are just setting certain states, saying that I'm going to be using some vertex attribute, geometry attribute, and normal attribute. So this is what I'm telling OpenGL, enable those use of vertex and normal data on the GPU side. And then bind buffer, saying that now I'm pointing to this vertex buffer object in the GPU, and then saying that these are my vertices. My vertices are in this, since this is the current bound buffer, this vertex pointer understands that, oh, this is where I'm going to find whatever the current buffer is, this is where I'm going to find this data. This last parameter, actually, this vertex pointer is sometimes used to point vertex data on the CPU. In that case, this last pointer is a pointer to an array on CPU memory. But when it's 0, and when there's a current bound vertex buffer object, it understands that, oh, okay, the data actually is on the GPU side. So these may be quite complicated when you're first new to these things. That's perfectly normal. As you work more, I mean, for the assignments, for example, you don't need to learn more about these things because you can use these programs as templates. But understanding what's going on behind is sometimes important to debug your programs. So you will need to take a look at some manuals or tutorials on OpenGL and these programmable shaders if you want to dive deeper into these. One good tutorial on this vertex buffer objects, let me show you vertex buffer objects. There's a tutorial. Yeah, some useful links about OpenGL. I think it's this one. I'm going to share. So this is a post that I did last year, I think, but I'm going to also have this. This CENG from Canada has a nice set of tutorials, which I think. Let's see whether that's still on. Yeah, so OpenGL vertex array. So it talks about this immediate mode. Take a look at the following code to draw a cube with the immediate mode. It shows the winding order. So this is a really nice tutorial page which shows how this GL triangles work, and also how we this is not the most efficient way, how we can use the vertex array functionality, the second one in the middle that I have shown you here, GL vertex arrays. It talks about this functionality here on this website, how you're going to do that and reduce the vertex data is still in memory. As you can see, you enable client state. I'm going to be using my vertex attribute here as an array, and with the same function called GL vertex pointer, in this case you see that it's actually the last parameter is a pointer to a vertices array in our on the CPU. So this is how you can reduce the entire you can draw this many triangles, 36 divided by 3, 12 triangles, 6 sides. Cube has 6 sides, so every side is drawn by 2 triangles, so 12. With this is the number of vertices you write here at the end. With a just single function call, you'll be able to draw 12 triangles instead of, so it's just for the same example, how we can reduce the number of function calls with vertex array is written here. It also talks about how draw elements, what is the difference between draw arrays? Draw arrays directly get the triangle vertices 3 by 3, with draw elements, we can have indices of these vertices here. Instead of the vertices now, there are 8 of vertex coordinates because cube has 8 corners, right? A cube has 8 corners. We just need 8 of vertex coordinates. In this one, there are 36 vertex coordinates because we are going to be drawing triangles 3 by 3. So this vertices array contains 36 floating point, actually 36 times 3 XYZ coordinates. And here we just need 8 vertices, and then we can specify those triangles which the vertices are shared by different faces, and we can write our indices like this, just like this face index face representation. We can have indices as integers like this, and OpenGL allows drawing of the triangles with this draw elements function. Instead of using GL draw arrays, we can say, okay, these are my vertices and here are my indices. Now I'm going to draw these 36 again. I'm going to draw 12 triangles, but now I will be using these indices to refer to those vertex coordinates. So this is a really nice tutorial which shows the vertex array and also the vertex buffer object, the most efficient version, how we can this GL buffer, GL bind buffer, GL buffer data. This is a really nice tutorial that explains how these functions work, what are the parameters. So for example, we had used this static draw, but there are other usage flag, and what those usage flags mean. There are different ways. So these tutorials also show different uses of vertex buffer objects and pointers. So I'm going to share with you these links. Let me just right now copy them on the chat box for now, but I'm also going to send them in the announcement on OpenGL. All right. So yeah, vertex array, a single version. So let's quickly go over the slides before the break, but I already talked about most of the things. So instead of many function calls, we can use this vertex arrays to send in one function call. In vertex arrays, we have this GL vertex pointer function, number of coordinates per vertex, type of each coordinate. So the stride is used to indicate the byte offset between consecutive vertices. So it's interesting. Let me talk about this a little bit. So sometimes when you have your data, instead of having, there are different ways you can send the normal data, color data, or vertex data and store them in an array. One way to store is to use separate arrays for vertices, normals, and colors. But you may also have a single array in which you have the XYZ coordinates for the first vertex followed by the normal vector of the first vertex, nx, ny, and z. And then nx1, ny1, and z1. And then the coordinate of the second vertex, x2, y2, z2, and x2, ny2, and z2. So you may actually have your data in memory like this: coordinate normal, coordinate normal, coordinate normal. So this stride function, stride parameter tells you between two consecutive vertices coordinate data, you have to jump, for example, whatever 3 times size of float, whatever the size of float is. If this nx, ny, and z are float, you have to jump this much to get to the next coordinate data. So this is what this stride is for. Okay, so this stride tells us this is the byte offset between consecutive vertex data. If you have some additional data in between them, it's not packed. If it's packed, the stride will be 0. Okay, stride is 0 when your vertex data is packed. There is nothing in between. It's just vertex geometry data. And this pointer here, as you can see, is a pointer to the vertex position data. In the case of vertex arrays, this will be a pointer to somewhere in CPU memory. in the case of vertex buffer objects, we just give 0 for this because we have, if we don't have a pointer directly to the GPU. And why don't we give then, for example, VBO index, for example, or VBO object, some vertex buffer object ID, because we don't send it as a parameter, we send it 0 here. Before calling this function, we bind that buffer as the current buffer. Instead of sending as a parameter, those integer handles are not used as parameters here because 0 signals something specific. If we give some non-zero data here, for example, if you give your VBO and it happens to be 6, for example, it will be treated by this GL vertex pointer function as a pointer, which is non-zero, which may be the 6 may be an address to some CPU memory. So in order to not confuse that, this 0 is treated like a special signal saying that, oh, okay, I have null here in this pointer vertex data. So the user probably, the programmer probably at this point is trying to use the vertex buffer object. So let me look at what is the current bound buffer object. This is where I'm going to put my data on the GPU. This is what the GPU is saying when it sees this function. So yeah, vertex array, vertex attribute pointer. So here we use vertex coordinate, the different normal value, color value. In modern OpenGL, instead of using when GL vertex pointers sends the vertex coordinate data, but in modern OpenGL, all these coordinate, normal value, color value, it may be something else for a vertex. The vertex may have many different parameters that are not defined in classic OpenGL. So in order to give more power to the user, in OpenGL, in modern OpenGL, all these vertex data, normal data, they are not named anymore. They're just named as a generic name as attribute. That's just attribute of a vertex. So so you just say vertex attribute pointer, and however you are going to use that attribute you are going to specify it in the programmable shader that you write. Okay, so you're going to so as I said, in modern OpenGL, this vertex color or normal or coordinate data are treated as generic attributes that the programmer handles in the programmable shader. And with the draw arrays, we just use a single GL draw arrays function, or we can use draw elements function if you're using indices. We have seen this example. And yeah, when we're drawing with vertex arrays, the vertex attribute data is copied from the system memory to the GPU memory at every draw call. So at every one of these either GL draw elements or GL draw arrays call, at every frame, as I said here, the entire data, as I said here, the data is copied at every frame with vertex array. But we still, the efficiency compared to immediate version is that we just have one function instead of many GL vertex functions. Okay, now again, to make it even more efficient, we use vertex buffer objects in which we don't do the copying at every frame at all. We get our generate buffers function, we get our buffers, we bind those buffers. These were the examples that I showed you, and the buffer data functions are used to copy the data to the GPU. When we so this is the allocate memory for us and copy. So with this single function call, the memory allocation and copying of data on GPU memory is done. So this is a repetition of what I showed you in the code example. So I'm skipping this part as well. So here are some explanation of what these parameters are. Attribute size. So actually they're not in their correct places. So this is the size. This is the attribute data pointer. This is the index size and index data pointer here. So after the copying is done, we can actually free the memory on our CPU because the data is copied to the. After these functions complete, the data is sent and copied to the GPU. So you can safely delete or free your memory on the CPU. And after that, drawing is very similar. So here the pointer, the 0, is actually used as offset to vertex position data. So when it's non-zero, actually it's treated as not a CPU memory. You can actually have non-zero value in the pointer. It means that you're not going to start at the beginning of your buffer object. You will start at this position. So it indicates the starting position on the buffer object in terms of how many, not how many bytes, but how many data points, I guess. So if you give, for example, 4, it will start at the 4th floating point value. The draw elements function is the same. Okay, so this OpenGL makes, so this vertex pointer and draw elements, the last parameter is sometimes treated as pointers, sometimes as offset, as I said. And OpenGL makes this decision if a non-zero name is bound to GL array buffer. When you have a GL array buffer, if a non-zero handle is bound to current array buffer, it will use the last parameter as the offset. If it's 0, it will use it as a pointer to the CPU memory. So they're similar. So in terms of performance comparison, this armadillo model composing of 200,000 triangles, it's drawn in 4 distinct locations, resulting in almost 1 million of these triangles. Ozoja did this test on his machine, which had this graphics card, AMD Mobility Radeon, the model number. Using vertex buffer objects, the frame rate was about 100 frames per second. And using vertex arrays, which is the client-side draw elements, the frame rate was about 20 frames per second. So you get 5 times speed up if you actually avoid sending geometry data at every frame. So an increase from 20 frames per second to 100 frames per second immediately by just using vertex buffer objects sending the data onto the GPU side. So most modern games, modern graphics applications, they use vertex buffer objects for drawing complex models. And one example here you see is this table lamp that we drove here with these 2 function calls. It uses this vertex buffer objects idea to draw the table lamp. So if you want to see an example program that uses this vertex buffer objects, you can take a look at the spotlight.c example that I provided to you. Okay, so now this is before starting a new topic. How do we do transformation modeling, viewing projection transformations in OpenGL? Let's have a 10-minute break. I will stop recording now. And after the break, we're going to continue with how transformations in OpenGL. There are only a couple of slides before we continue with programmable shaders. Okay, I will stop recording now.